We have looked at factor theorem, fundamental theorem of algebra, and we have seen conjugate root theorem. Now let's look at irrational root theorem. In an equation with rational coefficients, irrational roots of the form a plus root b occur in conjugate pairs, where b is a positive integer that is not a perfect square. Understand this condition. B has to be a positive integer. Why? Because otherwise, because of the square root, we will get into complex numbers. And the other condition is that it should not be a perfect square, because otherwise, square root of B will not remain irrational. It will become a rational number. Now, let f sub n of x be equal to this polynomial, which is equal to 0, where all coefficients are rational. Suppose x equal to a plus root b is a root. How can we say that? Because the theorem itself says if irrational roots of the form a plus root b occur. Okay, so we are taking that as given. F sub n of a plus root b is equal to 0. So if we substitute a plus root b in place of x, we will get 0. Substituting x equal to a plus root b into the polynomial gives an expression involving root b. So in place of x, if we substitute a plus root b, we will get an expression involving root b. Since all coefficients are rational, the result can be written in the form a plus b root b equal to 0, where a and b are rational numbers. Look at it like this. Root b we have. Now, the square of that is equal to b. Cube of it is equal to b times root b. Fourth power of root b is b square. So, in general, root b to the power of an even number is equal to b to the power of m. And root b to the power of an odd number is equal to b to the power of m times root b, where m is a non-negative integer. Because as we keep going along substituting, the powers will go, keep reducing by 1. So it will keep shuffling between odd and even powers. So therefore, every power of root b can be reduced to either a rational multiple of 1 or a rational multiple of root b. So here b and b square are rational multiples of 1, and the others are rational multiples of root b. Hence, the polynomial can always be written in the form a plus b root b, where a and b are rational numbers. Since root b is irrational and a and b are rational, the only way a plus b root b is equal to 0 is true if a is equal to 0 and b is equal to 0. So now let's substitute x equal to a minus root b into the polynomial, because this is the crux. This is what we are trying to prove. Replacing root b by minus root b changes the sign of every term containing root b. Since both a and b are 0, we again get f sub n of a minus root b is equal to 0. So if a is equal to 0 and b is equal to 0, that means the whole expression becomes 0. Therefore, if a plus root b is a root, then a minus root b is also a root. Thus, irrational roots of the form a plus root b occur in conjugate pairs, provided the necessary conditions are satisfied. What are the conditions? Rational coefficients and b is a positive integer. That is not a perfect square. Now, we have previously applied the same ideas without using these theorems. But our examples were limited to quadratic and cubic equations. However, these theorems are valid for polynomial equations of any degree. So that was irrational root theorem. That's it for now.